Welcome to The Explainer. Today we're going to peel back the curtain on the massive cost and, frankly, the mind-boggling complexity behind training the AI models that are literally changing our world. And here's the kicker. It all boils down to some surprisingly simple napkin math.
All right, let's just jump right in with a question that AI engineers are wrestling with every single day. Imagine this. You've got a massive 70 billion parameter model, and you need to feed it 15 times trillion tokens of data. And you can just think of tokens as like pieces of words. So the big question is, how long is that going to take?
The answer? It's about 1444 days. Yeah, almost 5 months. And get this, that's only if you're using over 1,000 of the world's most powerful GPUs, all running 24/7. It is an absolutely colossal undertaking. But how? How can anyone possibly predict that with any kind of confidence? Well, it's definitely not a wild guess. It's the result of some really elegant, surprisingly simple napkin math that basically powers the entire industry. And that's what we're going to unpack today.
All right, Section 1, the billion-dollar question. So to answer these huge questions, we really need to get our heads around the two fundamental resources that every single AI model just eats up: memory and compute. You can think of them as the two sides of the same AI coin.
So let's dive into Section 2, what I'm calling AI's memory game. We'll start with memory, and trust me, this isn't just about how much storage you have. It's more like a high-stakes game of trade-offs, a constant battle between the quality of your numbers and the raw speed of your calculations.
So this whole journey into memory, it really starts with one fundamental building block, the tensor. Seriously, you can think of it as the atom of the AI universe. At its heart, it's just a container for numbers, kind of like a big multi-dimensional spreadsheet that holds absolutely everything the model knows and everything it's processing.
Okay, but here's the thing. In the world of AI, not all numbers are created equal. You've always got to make a choice. On one hand, you have something called float32, or FP32. Think of this like a super high-resolution photo. It's incredibly precise, the gold standard, but it's big, taking up 4 bytes, and it's slower. On the other hand, you've got bfloat16. This is your good enough photo. It's half the size, so it's way faster and uses less memory, but, you guessed it, it's less precise. So engineers do a clever trick. They use the faster, smaller bfloat16 for all the heavy lifting calculations, but they keep the final, most important knowledge, the model's weights, in the super precise FP32 format.
And this right here reveals the hidden cost of memory. See, to train just one single parameter, you don't just store it once. Oh no. You need a copy for the parameter itself. You need another copy for what's called the gradient, which kind of tracks which way the model should learn. And then you need 2 more copies for the optimizer state, which helps the model learn smoothly and not go off the rails. So when you add it all up, for every single parameter you want to train, you actually need about 16 bytes of memory. That is a massive 16x multiplier.
Okay, Section 3, counting the calculations. So now that we've got a grip on the memory side of things, let's look at the engine of AI training: raw, unadulterated computational power. So how do we actually measure the work an AI has to do? Well, we use a unit called a flop. That stands for floating point operation. You can just think of it as one single math calculation, like one addition or one multiplication. The total number of flops, then, tells you the total amount of raw work your model has to crunch through to get trained.
And you might be wondering, where do all these trillions of flops even come from? Well, here's a quote that says it all. No other operation you encounter in deep learning is as expensive as matrix multiplication for large enough matrices. And that's the key. The vast, vast majority of all that work comes from this one single, incredibly intensive operation. It's the absolute bread and butter of deep learning.
And this is exactly why the hardware arms race is so ridiculously intense right now. Just take a look at the compute power, measured in T-flops, that's trillions of calculations per second, for 2 generations of NVIDIA GPUs. The A100 GPU clocks in at 312 T-flops. The next generation, the H100, is almost at 1,000. That's a massive 3x leap in raw power, and it's all designed to do one thing: crush those matrix multiplications faster and faster. But listen, just having a super powerful GPU isn't the whole story. You've got to use it efficiently. It's like having a Ferrari engine. If you don't know how to drive it, you're not going anywhere fast. And this is measured by a super important metric called MFU, or Model Flops Utilization. Think of it as the fuel efficiency rating for your AI training. It basically asks, how much of the hardware's theoretical power are you actually using? Believe it or not, getting a score over 50% is considered really, really good.
Okay,
Section 4, the true cost of training. We've talked about memory, we've talked about compute. Now it's time to put it all together. This is where we finally reveal that secret rule of thumb for estimating the true cost of training these massive models.
You see, training in AI isn't just a single step. It's really a two-part dance. First, you have what's called the forward pass. This is where the model looks at the data and makes a guess. This step costs about 2 flops for every single parameter in the model. But then comes the most important part, the backward pass. This is where the model looks at its guess, figures out how wrong it was, and actually learns from its mistake. And this part, the learning part, is way more expensive. It costs double at about 4 flops per parameter.
So let's do the simple math here. You've got 2 flops for the model to make its guess, and 4 flops for it to learn from that guess. You add them together, and you get the magic number, 6.
And there it is, the simple yet incredibly powerful formula that the entire industry uses. The total training flops you'll need is roughly 6 times the number of parameters in your model times the number of tokens you train it on. That's it. That's the napkin math. It's what lets engineers look at a model on a whiteboard and get a pretty darn good estimate of how much time and money it's going to cost to build.
All right, final section, why this matters. And look, understanding this simple math is so much more than just a neat party trick. It really gives you a powerful new lens for looking at the entire AI landscape, from the crazy headlines you see every day to the billion-dollar business decisions being made behind the scenes.
Because now, with just these few building blocks, you can really start to grasp the deep economics and engineering challenges at the heart of AI. You can now estimate the time and cost to train a model yourself. You understand why there's this insane hardware arms race for more powerful GPUs. You can see that constant painful trade-off between speed and precision. And most importantly, you know why efficiency, getting that high MIFU, is absolutely the name of the game.
And all of this leaves us with a really fascinating, critical question for the future. As these AI models just keep demanding more and more resources, getting bigger and more expensive, is the next big breakthrough going to be a smarter model